All right, welcome to today's lesson number 3 on atomic models. So today we're going to be looking at kind of the role of evidence in the development of atomic models. So kind of looking at what experiments were used, and then we're also going to try and look at the progression here as to how we've started to understand the atom and the subatomic particles that create the atom itself. Okay, so this is actually one of my favorite topics, I think, of the chemistry unit. I do find the history of science to be something that's really interesting, but also something that we tend to take for granted. We kind of utilize a lot of the technologies and things like that we have, but we don't often go back and ask ourselves, where did this come from? Somebody had to dream up this idea at some point, and how did they figure it out? So we're going to go through just a little bit of the history of the atom today. We're going to look at 4 different models. If you go on to take Physics 30 at some point, you're going to go a little bit further into each of these models, and you'll get a little bit better understanding even as to kind of how they all link together. But for right now, we're just going to take things at kind of an intro level. So again, we have 4 scientists, and we're going to get kicked off at John Dalton, 1803, when he comes up with the billiard ball model. So John Dalton is the only one of the 4 scientists that we're going to look at that doesn't really have a specific experiment attached to his work. So through a variety of different experiments and observations that he made, he kind of came up with these following 5 ideas. So let's fill in this first blank here. So by combining many observations, okay, he was able to come up with these conclusions. So out of these 5 conclusions, after I'm going to get you, once I've kind of explained each one what he thought, I'll get you to pause the video, answer the prediction at the bottom as to which ones you think maybe are still correct. And then after that, we'll go through the answer to that as well. So the first thing that he said is all matter is made up of tiny particles. Okay, so basically you have to think about dating yourself back 220 some years ago. People's understanding was very, very, very minimal. A lot of people never would have got to go to school. Lots of people weren't able to read or write or anything like that. So I also like to take an appreciation for that. It's not out of the ordinary, even if you were to ask your grandparents and things like that, that potentially some of them grew up in houses without running water. They might have had to haul water. Maybe they didn't have electricity. I know my own father, when he was younger, didn't have electricity in some of the houses that he lived in Saskatchewan. That was in the 1960s. So to think to date all the way back to 1800, we really have to put ourselves into that frame. But people would have viewed things as just being a single piece. So for example, you look at the top of your desk, people would have viewed that as a piece of wood. It took the scientists to say, yes, that is a piece of wood, but if we could really zoom in on that, what we would see is millions and millions and millions of these little things, these little particles called atoms. So this was one of John Dalton's big things. He said that even things that look large are actually made up of tiny, tiny little blocks called atoms. Okay. He said that atoms cannot be created, destroyed, or divided into smaller particles. So he just said the atom is the fundamental building block. So the easiest way for us probably to think about this now is to think about Lego. Okay, when you have a piece of Lego, obviously you could saw it in half or something like that, but for the most part that piece of Lego is indivisible, so you can't break it up into anything smaller, but you can use it to build bigger things. So that's kind of how he would have viewed the atom at this point. So he said all atoms of the same element are identical in mass and size. Okay, so every single copper atom looks the exact same. Every single hydrogen atom looks the exact same in terms of mass and size. And he said atoms of different elements are different in mass and size. Next up, he said the compounds are formed when atoms of different elements combine in fixed proportions. So what he meant by this was something such as water is 2 hydrogens and 1 oxygen, H2O. He said you can't have decimal numbers, you can't have 2.5 hydrogens getting together with 1 oxygen, because up here remember that he said that they cannot be divided into smaller particles. So there's no way to have a half an oxygen. You have one oxygen or two oxygens, so no decimals. And these chemical reactions change the way that atoms are grouped and partnered, but the atoms themselves remain the same. So what he was saying basically is if I take water, which is H2O, and I react it, actually let's pick something else. Okay, we're going to pick something else. So imagine taking sodium chloride, which is NaCl, and I react it with magnesium phosphide. And I'm going to teach you how to do this later in the chemistry unit here, but right now I've drawn a reaction between sodium chloride and magnesium fluoride. I think I maybe said phosphide earlier, but magnesium fluoride. So if these two react, what I'm going to get is I'm going to get a little switcheroo going on here. Okay. So what he said is basically the magnesium that we had on this side is still the exact same magnesium on this side. We just have now switched its partner. So the way it's grouped and partnered is different, but the magnesium itself hasn't changed. We just basically watched it get up and walk. So imagine like if we were at a school dance and we have like, some people dancing together, different song comes on, they all pick a different partner to dance with. They're still the same people. So they themselves haven't changed. They're just changing who they're dancing with. And the same thing happens with atoms. So we can think of the atoms as all being like one big dance. Okay. Now, in terms of the prediction, which of those 5 statements do you think above are still currently true? Okay, and I'll get you to pause here and give it a go. Okay, so welcome back from your pause. We're going to kind of go through 1 through 5 here. So all matter is made up of tiny particles called atoms. 1 is true. Okay, things are made up of atoms. We know that. Number 2, atoms cannot be created, destroyed, or divided into smaller particles. True is false. And we're going to talk about what those particles are coming up here in some of the next scientists. Number 3, all atoms of each element are identical in size and mass. That's also false. And we're going to learn about something called isotopes here in a couple days. So an isotope is just the same element, but it has a different mass. And again, we'll get to that more later. Compounds are formed when atoms combine in fixed proportions. That's true. And number 5, chemical reactions change the way that atoms are grouped or partnered. Absolutely true. Okay. Now, depending what kind of chemical reaction you're talking about, maybe 5 you could also kind of view as false. But for the most part, what we're looking at in this course, 5 is also going to be true. So, I mean, when you look at it, 3 for 5 from a scientist in 1803 trying to define matter, that's pretty darn good. He's got my props for sure. Okay, so this brings us to J.J. Thomson. So we're looking at like 1894. So I mean, almost 100 years have gone by, and Dalton's atomic model has stood true. So J.J. Thomson used cathode rays to discover the electron. Okay, so this is our first mention of like a subatomic particle. Okay, so when we say subatomic particle, so the ones that we're going to be talking about in Science 10 are protons, electrons, and neutrons, but the electron is kind of the first one that we found. So I'm just going to walk you through this diagram here as to what happens. So if we look at A, we have a source of high energy electricity, okay, and then we have a cathode, which is this piece of metal, and we have an anode. So notice how the cathode's negative and the anode is positive. So in electricity, a positive charge and a negative charge attract. Okay. A positive and a positive repel, so they don't want to be by each other, and a negative repel. Okay, so opposites attract. So what happens is you hook this like high energy electricity up to this metal, and now when you give things energy, like think about a little kid, for example. If I asked you, what does it look like when a little kid has a lot of energy? You'd probably tell me either like, man, they're like screaming or like shouting, but like most often you're thinking about them just running around. So when things get a lot of energy, they tend to move more. And the same thing happens with the electrons at the cathode. Okay, so over here on the cathode, as these electrons get enough energy, eventually they break free. Now some of them are going to come, because again, remember, they're electrons and they're negatives. They're going to be attracted to this positive over here. Some of them are going to crash into that plate, and that's fine. But others are going to make it through the middle, and they're going to just travel until eventually they hit something. Okay. Notice how this down here says to a vacuum pump. In science, vacuums are really important, and they're not like, the Dyson that you might clean your floor with. A vacuum just means like that there's no air. It's like empty space. Okay. So much of space itself, like when we think about out by the planets and things like that, is actually a vacuum where there is no air. And that's why lots of times we say like sound can't really travel through space. So the sun should be making a ton of sound. Like there's violent reactions happening in the sun, but we don't hear it because sound needs air or a medium to travel through, as where light doesn't. So we get the light and we get the heat from the sun, but we don't get the sound, which is kind of cool because we don't want to listen to this massive explosion in the sky all day long. So anyways, back to my cathode ray here. The cathode gets really good, like a lot of energy given to it, and these electrons start breaking free. So what J.J. Thomson, he didn't invent the cathode ray, he just utilized it. What he noticed is that if we come over here to C, when you have a negative plate and a positive plate, so what he did was bring some more electric charge nearby. He noticed that this thing bent downwards, and it bent towards the positive plate. So again, remember that opposite charges attract. So if it's going to the positive plate, this stream must be negative. So what he starts saying then is, well, these negative charges had to come from this cathode, which was this metal. The metal's made up of atoms. So somewhere in that atom, there has to be a negative charge. It couldn't just magically appear out of nowhere. So if the metal's made up of atoms and the metal gives off the negative charge, the atoms must have a negative charge. And just like that, we have the birth of the electron. So let's go through and fill in some notes and see if there's anything else that I can add to this. So how does a cathode ray tube work? You take a high energy power source, such as like a really strong battery or generator, and you hook it up to a piece of metal. Now, the metal we use has a low work function. When we talk about a metal, and this is kind of more of a physics 30 thing, but when we talk about a metal, the work function talks about how tightly it can hold on to its electrons. So a low work function is really weak at holding on to its electrons. So if you think about the whole point of this is you put energy towards a metal, so that way its electrons, like it gives off its electrons and they all break free. You don't want it to hold on to them really, really strong. Because if it does, it just means you have to put more energy to it, and then that's a bit more of a hassle. So you pick a metal that like is super easy to get electrons off of it, so something with a low work function. So the work function talks about how strongly a metal can hold on to its electrons. So the power source starts to heat up the metal, and electrons gain energy and start moving faster. So again, remember the kids, super hyper once they get energy. So the anode is positively charged. Okay, so the electrons are attracted towards it. Once they get enough energy, they break free and they're going to travel towards that anode. So some of them crash into it, while others pass right through the hole that you see in the diagram, and then they travel towards the end of the tube. Okay, so in terms of this next paragraph, it says that Thomson did not invent the cathode ray tube, but he was able to show that the beam created could be deflected by an electric field, by that like positive and negative that he brought in at the end. So you notice that when you brought something positive and something negative near the cathode ray tube, the beam always went towards the positive. Okay. So Thomson knew and then was able to conclude the following. So he knew that the metal he used is made up of a bunch of atoms. Okay, we have Dalton to thank for that one. The beam that came from the metal was negatively charged, so there must be negative charges somewhere in the metal, and the metal itself is neutrally charged. Okay, so if he knew there was a negative charge, but the metal itself wasn't negatively charged, he thought, well, like, let's talk about adding integers for a second. Positive 1 plus negative 1 equals 0, or neutral. Okay, so he said, if I know this exists, and I know that overall the metal's neutral, then this must also exist somewhere. He just didn't know what it was. He never was able to find the positive charge in the atom. So he just concluded that the atom was a sphere of positivity and the negative charges were embedded in it. So we call this the plum pudding or the raisin bun model. So if we take a look at this diagram right here, we see this kind of like positive sphere, which is some like negatives implanted into it. So that was Thomson's idea. So he was correct that electrons exist. They just don't exist inside, and the positive isn't just like this sphere. So he was kind of correct, but either way, moved us forward for sure. Cathode ray tubes would eventually become the foundation for creating TVs. Okay, so although this is before your time, when I was your age and in high school, most houses that you would have went to like still had one of these what are called cathode ray tube TVs, or CRT TVs. Now, if there's any of you like kind of game nerds out there like myself, if you think about the first NES, like Nintendo Entertainment System, there was that game called Duck Hunt. And it used that orange kind of like zapper gun. Now that gun was set up to work on these types of TVs. If you've ever landed one of those guns and tried to use it on like a modern flat screen, whether that be like plasma, LED, etc., like you would see that that gun doesn't work. And we'll talk more about that when I get back. We'll also watch these two videos when I get back to class as well. It just kind of explains how a cathode ray TV works, and then shows you kind of a video in slow motion. So super cool. But I'd like to be there kind of when we roll through that, just so I can add a few things to it. And then just kind of a random fact for you, like these CRT TVs were like late 2007, early 2008. So again, to give you some context, I graduated from high school in 2008. And that was kind of when Sony stopped producing these things. And just better technology existed. But we'll talk more about that when I get back. Okay, so that brings us to Ernest Rutherford. So we're looking at right around 1909 now. Okay, so a little more than 100 years ago. Again, still super impressive that somebody was able to piece this together back then. So what he did is he directed a stream of alpha particles. Now, if you take Physics 30, you'll talk about alpha particles quite a bit. You'll use them in lots of example questions, but basically what's going on is we have like in this box, we just have a decay reaction going off, and it's just giving off these alpha particles. Alpha particles are basically just like kind of a helium nucleus, but again, not really important for what we're doing here. So just know that he used alpha particles, and that's good enough, okay, and that they were positively charged. So he directed them towards a thin sheet of gold foil. If you take a look in this diagram, we can see the thin sheet of gold foil. Okay, we can see the path of the alpha particles coming inwards to this device. And then the speed of them, that's 20 million meters per second. Okay, so I want you to just like stop for a second and think about that. 20 million meters per second. Like, that is astronomically fast. Okay, not near the speed of light, but very, very, very fast. Okay, so imagine like trying to work with something that moves that fast, and that's this small. These people were absolutely brilliant, and this is very difficult to do. So we definitely kind of owe them a major thanks, albeit they're not around to hear it. So the current belief of the atom was that it was mostly empty space. So he expected as he's shooting these alpha particles, they would just go straight through the foil. He thought that the ones that would hit an atom would just deflect a bit. Okay, so when we talk about deflect, we just mean change their path a little bit. So if we look at this diagram down here in the bottom corner for a second, this is kind of what he thought. mostly empty space. Notice how most of the arrows are going right through. Okay, we have one here that kind of comes in, clips this a little bit, bends a little bit. So that was kind of his prediction. So if we go back up to this other diagram here, we can see that most of them end up, hitting the back or making small deflections. But what he didn't see coming were number 5 and number 6. Okay, so a few alpha particles actually like hit the foil and bounced almost straight back. Okay, which he never thought was going to be possible. And then some of them also kind of just like hit and then like had a massive deflection. Like he saw minor deflections, like a little bit off course, but not like, a 90-degree angle, and definitely not coming backwards. Okay, so these were very kind of interesting to him. And there's a quote at the bottom here that this is an Ernest Rutherford quote that I just want to direct you to, like just to kind of let you know how crazy this would have been back in the day. Like he said, it's almost as incredible as if you fired a 15-inch shell. So like we're talking about basically like kind of a bullet at this point at a piece of tissue paper, so like a Kleenex, and it came back and hit you. So imagine like even just taking like a rifle out to a range somewhere, shooting it at like a piece of loose leaf or shooting at a piece of Kleenex, and then having it fly back at you. Like you would be absolutely amazed. And that's where Ernest Rutherford was at this point. So he came up with some conclusions from this. Okay, so remember, he took something positive, he shot it towards something, okay, and then some of them ended up getting repelled back, so it bounced off of it instead of just going through, and most did go right through. Okay, most went right through, but some ended up getting bounced back. So these were his observations, that some alpha particles got repelled backwards when they hit the gold foil. He also observed that most of the alpha particles went straight through, and he observed that none of the alpha particles got stuck to the gold foil. Okay, so he made 2 conclusions. So right now I want you to pause the video and see if you can draw a line between the observation and the correct conclusion that he would have made from that observation. Okay, and then we'll go through it together in a second. All right. So some alpha particles got repelled backwards. Okay, that would go with this conclusion right here. For that to be able to happen, the nucleus has to be positively charged and it has to be densely packed. Okay, imagine like running into something and then getting like shoved completely back. Whatever you ran into is going to be like pretty solid. So that's what he said. For this to actually hit and like bounce back like that, whatever it hit, very densely packed, and he also knew it had to be positively charged. If it was negatively charged, when you shoot something positive to it, it would just stick to it. It wouldn't get pushed backwards. Okay? Most of the alpha particles went through the gold foil. Most went through because most of an atom is empty space. Okay? With the electrons orbiting around the outside like planets. So he basically was saying we have something very dense in the middle, and then we have our little electrons kind of around the outside. Okay, where each of these dots are like kind of wannabe dots, I guess. Each of these dots are electrons. And then he said none of the alpha particles stuck to the gold foil. That was because the nucleus is positively charged again, like I kind of mentioned before. So we're getting a little closer to the image of the atom. Okay, so we have a positively charged center, and we have electrons floating around the outside. So remember, Thomson thought the electrons were inside. Now he's saying the electrons are on the outside. And that's Rutherford that's saying that. So this brings us on to Niels Bohr. Now, this is definitely not the last atomic model, but this is the last one that we're going to go through in Science 10. So we're looking at 1913, so not too long after Rutherford, but Bohr did agree with Rutherford in that he said the nucleus of the atom was positively charged and that the electrons existed outside the nucleus. However, what he said is that the electrons existed in set energy levels. Okay, so they weren't just like free to exist wherever they wanted. They had to exist in like specific energy levels. And if you take a look at the diagram over here, you can see what we're talking about. Now this here, we need to fix that up. I just noticed this should actually say Bohr. Okay. To make this conclusion, Bohr studied what colors and energies of light atoms are able to absorb. So I'm going to give you just a very, very brief physics 30 lesson here, and then we're going to call it good for this. So if I put an electron in this right here, this is a low energy level, and the further away from the nucleus I get are my high energy levels. Okay. Now, for an electron to move from a low to a high energy level, it needs more energy. Okay, it's in a very like cheap state and it needs to get out to the expensive ones. So if I take light and I crash it into this electron, the energy from the light can push the electron out to another energy level. Okay. Now, the electron's not going to want to stay there because it realizes that it doesn't belong there, and it's going to bring its way back down. To do that, though, it has to get rid of the energy. So what does it do? It just gives off the light that it absorbed to go out there. So it's basically like, you hit it with some light, you give it some energy, it leaves, it goes to the outside, and then it's like, yeah, I don't want to be out here. So it throws that light back out, and then it comes back. Now, what Bohr realized is that you can't just use any type of light. Only special colors of light and only special, what we say would be wavelengths or frequencies of this light will work. So he shone like hundreds of different colors of light at these electrons and realized that there was only very few times that energy actually got absorbed. So what he said is that however much energy the light had, if it worked, it must have corresponded to a certain energy level. And that is how he came up with his finding. Again, if you take Physics 30, we're going to go way further into depth on this, and it's actually very, very interesting stuff. So I would really encourage you to work your way into that course if this seems like something that you'd be into. Okay, so this brings us into the practice questions. Before you do this, there's another YouTube video on atomic theories. I would like you to watch that first. It's a little bit more concise than what I just went through, so just in case you need to hear it again, or just hear it in a different set of words. And I know that it's difficult here without having animations and more visuals and things like that. And you can't see, I'm constantly talking with my hands and making signs back here, but I know you can't see those. So check out this YouTube video. You can find it in Google Classroom on atomic theories. Okay, and then come back, and I'd like you to first label each of these diagrams as to which scientist you think each of these 4 diagrams best represents. Then you're going to look at these questions, and you're going to say, these are all quotes from scientists. Now, they're not actual quotes, they're quotes that I've made up, that I think the things that they would have said based on their beliefs. So when you read each one, just write down which scientist would have done that. And even if you want to just put D, T, R, or B, that's fine. Okay. And then on this question here, it tells us that oxygen has 8 protons, 8 electrons, and 8 neutrons. So you're going to draw what the element would look like from each of the 4 scientists according to their atomic model. So you need to think, this is what we know about oxygen right now, but that's maybe not what Dalton knew. Okay, so if you told John Dalton to draw you an oxygen atom, he wouldn't have drawn it with protons and electrons and neutrons because he didn't know that those existed yet. So you're going to draw, what did Dalton see oxygen looking like? And what did Thomson see oxygen looking like? So only include these things if the scientists actually knew about them. And if they did know about them, make sure you put them where they belong. Okay, so you're going to draw me a Dalton, a Thomson, a Rutherford, and a Bohr model. Okay, and here is the link to that summary I was talking about earlier. But again, it's going to be in Google Classroom for you. So I hope that this was helpful and a decent introduction. We will go through this a little bit more when I get back. But again, hopefully you were able to take something from this. Check Google Classroom for the rest of the instructions for this class if that's the reason why you're watching this video right now.